Imagine flying over the Mojave Desert at sunrise, where the first light touches one of the most powerful energy ideas ever proposed. Below you, the ground no longer looks like sand. From the air, it begins to look like glass. Millions of solar panels stretch across the desert floor, arranged in perfect rows that seem to run forever. From above, the landscape stops looking natural and starts looking engineered, like a machine built across the desert. This is the dream of a 10-gigawatt solar megacity, one enormous desert power complex built from sunlight. A project this large would not be a normal solar farm. It would be an industrial energy city. On paper, 10 gigawatts could rival the output of multiple conventional power plants operating at massive scale. It could send electricity toward major urban load centers across the American Southwest. Los Angeles, Las Vegas, Phoenix, and other cities would all seem within reach of this desert power machine. But there is one problem: America has never built a single solar megacity like this. Not because the sun is missing, and not because solar technology is impossible. The real challenge is hidden behind the panels. The real machine is made of inverters, substations, batteries, transmission corridors, grid studies, and control systems. This is MegaScale Engineering. To understand the project, we first need to understand what 10 gigawatts actually means. 1 gigawatt equals 1,000 megawatts, so this concept means 10,000 megawatts of installed solar capacity. That number is enormous, larger than most individual power stations on Earth. But installed capacity is not the same as constant output, and that distinction changes everything. Solar production rises in the morning, peaks near midday, falls in the afternoon, and disappears after sunset. The grid is far bigger than one project, even one this large, so engineers measure both power and usable energy. With a strong desert capacity factor, 10 gigawatts could generate tens of terawatt-hours each year. Now comes the land problem. Fixed-tilt solar could require tens of thousands of acres. Single-axis tracking systems increase energy yield, but they also require wider spacing between rows. The result is a footprint measured not in city blocks, but in dozens of square miles. That footprint needs access roads, maintenance corridors, fencing, fire breaks, drainage paths, and security zones. Below the surface, heavy cable routes must collect power from thousands of solar strings. On a satellite image, the desert looks empty. On an engineering map, it is crowded. Some land is protected, some is environmentally sensitive, and some contains cultural or tribal resources. Some terrain is too steep, too rocky, or too fragmented to support a clean utility-scale layout. Some ideal solar areas are simply too far from existing transmission lines and major electrical demand. That is why permitting becomes a system constraint, not just a legal formality. A solar megacity is not just a field of panels. It is an industrial city spread across the desert. At the module level, every panel is a small power source exposed to heat, dust, and sunlight. Tracker hardware adds motion, allowing rows of panels to follow the sun through the day. Desert heat can improve sunlight availability, but it also stresses electronics, cables, and equipment. Dust storms, soiling, and harsh weather create maintenance problems across a site this large. Even natural drainage matters, because desert washes can reshape how roads, trenches, and panel blocks are placed. When all these layers come together, the simple solar idea becomes a full engineering blueprint. Now imagine the land is approved, the panels are installed, and the sun is rising over the site. Sunlight hits each PV module, and the first electrical current begins inside the solar cells. That current is direct current, or DC, and it moves through the internal pathways of each module. Panels are connected into long strings, raising the voltage before power leaves the array. Those strings feed into combiner boxes, where many DC circuits are gathered and protected. Inside the combiner, fuses, breakers, and terminals organize thousands of small electrical paths. From there, heavy DC cables carry energy underground towards centralized inverter stations. Across a 10-gigawatt site, this underground cable network becomes a hidden electrical highway. The power then arrives at inverter stations, where the first major transformation happens. The grid cannot use raw DC power from solar panels. It needs synchronized alternating current. Inside the inverter, power electronics convert DC into AC while controlling voltage, frequency, and phase. Cooling systems remove heat from the electronics because wasted heat becomes a major reliability issue. Many inverter outputs must synchronize into clean waveforms before joining the wider grid. At this scale, there is no single giant inverter. There are thousands of inverter blocks. Each block works like a district in an electrical city, coordinated by software and sensors. After inversion, medium voltage transformers raise the voltage for movement across the plant. Collector circuits gather power from many inverter blocks and route it toward the main substation. The substation is where the solar farm becomes part of the larger transmission system. Large step-up transformers raise voltage again so electricity can travel long distances efficiently. Busbars, breakers, switches, insulators, and gantries direct power through the substation safely. High-voltage breakers must isolate faults in milliseconds before one failure spreads through the system. Protection relays watch the electrical network constantly, looking for abnormal currents, voltage shifts, and faults. SCADA systems form the nervous system, monitoring the plant from panels to batteries to substations. A 10-gigawatt plant is not a small disturbance. If it trips suddenly, the grid feels it. Traditional power stations use spinning machines, and their physical inertia helps stabilize frequency. Solar farms connect through power electronics, so their behavior is shaped by software and inverter design. Modern inverters can support the grid, but those functions must be modeled, tested, and approved. Grid-forming inverter technology can help create stable waveforms instead of only following the existing grid. The grid does not only need watts. It also needs voltage support. Real power does useful work, reactive power supports voltage, and apparent power combines both. These relationships form the power triangle, one of the hidden foundations of AC power engineering. At MegaScale, voltage stability becomes a project-defining constraint, not a minor technical detail. Capacitor banks can provide local reactive power support and improve voltage behavior. Reactors help absorb reactive power and control voltage rise under certain operating conditions. STATCOM systems use power electronics to respond quickly to changing grid conditions. Harmonic filters clean distorted waveforms before they create heat, losses, or equipment stress. Synchronous condensers can add rotating inertia and short-circuit strength to inverter-heavy grids. Together, these systems form the power factor correction and voltage support layer of the solar megacity. Then comes the biggest wall of all, the high-voltage transmission leaving the desert. Power must move across long corridors from the best solar resource areas to distant load centers. When too much power reaches a weak grid node, congestion appears and useful energy can be trapped. That is curtailment. The sun is shining, the panels are ready, but the energy has nowhere to go. Even if transmission is solved, solar still has a timing problem. Output rises toward noon and falls sharply at sunset. At midday, a huge solar plant can create more power than the local grid can use. In the evening, city demand rises just as solar generation begins to disappear. This creates the storage cliff. The bigger the solar plant, the bigger the sunset problem. Battery storage turns midday solar energy into evening grid support. At noon, energy flows into battery containers through power conversion systems and transformers. After sunset, the batteries discharge back into the grid while the solar panels are dark. But battery yards also need cooling, monitoring, safety systems, and careful thermal management. Spacing and fire separation become part of the engineering design, not optional details. Software must decide when to charge, when to discharge, and how to support voltage and frequency. So why has America not built one giant 10-gigawatt solar megacity in the Mojave? Because one giant project creates one giant land problem. It also creates a concentrated transmission problem, forcing massive power through limited corridors. It creates a concentrated storage problem, requiring an entire battery city beside the solar field. And it creates a grid stability problem that must be solved before connection, not after operation. The more practical future is distributed, many large solar plants connected across multiple regions. Solar plus storage clusters can be placed closer to existing substations and transmission capacity. Regional balancing lets solar, wind, batteries, substations, and cities share the burden together. Advanced inverters may help future renewable plants behave more like stable grid resources. Smart substations, sensors, and control systems will coordinate the grid faster than humans can react. The 10-gigawatt desert may never exist as one machine, but pieces of it are already being built. Panel by panel, battery by battery, substation by substation, the solar megacity is becoming a distributed system. At Megascale, the question is never only whether we can build it. The real question is whether the system can survive it.